So what kinds of matrices can we invert? Well, what are we starting with in this example? Here, this A is just an identity matrix. And if A is the identity matrix, what does A inverse turn out to be? Also identity matrix. Is that surprising? Not really. Because if what the identity matrix does to a vector is nothing, then to undo what that does, we need to do nothing. There's nothing to undo, right? If A leaves vectors alone, then its inverse also leaves vectors alone. It does nothing. So that's not too terribly interesting. But if we decide to mess around with some of the coefficients, we can maybe find some other interesting matrices to invert here. So let's kind of tweak our matrix here. So the first column is, I don't know, 1, 2, 3. Actually, we looked at a matrix like this just the other day. Let's look at 1, 2, 3, 4, 5, 6, 7, 8. And just for a moment, I'm going to leave this last entry here at 8. So here's a matrix. And here's the inverse over here on the right. Do you notice anything about this inverse that didn't happen with the last examples that we've seen? It's got some fractions in it, right. So one of the things you'll notice about inverses is that it's kind of rare for the inverse of a matrix to be whole numbers, even when the original matrix is whole numbers. And it, I guess, shouldn't be too surprising because we're thinking about this as being a way of dividing by a matrix. And anytime you're dividing by whole numbers, you can't really expect everything to work out evenly all the time. So for this reason, occasionally the computations to get a matrix inverse can get a little hairy because you end up having to carry some fractions through a lot. But still, this matrix is invertible because if we imagine, we're not going to do all these steps, but if we imagine augmenting this matrix with an identity matrix on the right, 1, 0, 0, 0, 1, 0, 0, 0, 1, that we could do enough elementary row operations to get this down to the identity matrix on the left, and then what's on the right would be our inverse. But this relies upon an important fact. Namely, in order for this to work, how many pivots does A have to have in this example? It's got to have 3 pivots. Because after all, it has to be a 3 by 3 identity matrix. We actually talked about this yesterday, that in order to be an invertible linear transformation, an invertible transformation has to be both one-to-one and onto. Those are just principles of function theory in general, right? Stuff from your proofs class, Proofs in Logic, Math 180. So the matrix then also has to reflect the properties of being one-to-one and onto. From yesterday, what does it mean for a matrix to be one-to-one? How do you tell when a matrix represents a one-to-one transformation? This was Alex and Zach's group, I think. No, sorry, it was your group. You did not too. It was Jocelyn and Catherine. One-to-one.
Have all pivots?
All what have pivots?
All the columns have pivots.
All the columns have pivots. Exactly. And the reason we need all columns to have pivots is that we want not to have what?
Free variables.
Exactly. No free variables. Because free variables are the source of non-trivial solutions to the homogeneous equation and therefore non-unique solutions to AX equals B, which is what we don't want for a one-to-one transformation. So we need to have a pivot in every column. And what about onto? Right. Because if all the rows have pivots, this means that every equation has a bound variable in it. Each equation has a bound variable, and therefore we're never going to get some untrue statement like 0 equals 27 in it to make it inconsistent. So the system AX equals B is always consistent when each equation has a bound variable, and it happens when all rows have pivots. So in order to be invertible, we need both of these to happen. And the only way for both of them to happen is that every column and every row has to have a pivot. But since we can have at most one pivot in every row and column, the reduced row echelon form can only be the identity matrix. So the first observation about what it means for A to be invertible is that the reduced row echelon form, in other words, the end product of all of your row operations, must be the identity matrix. Otherwise, this algorithm wouldn't work, because this algorithm relies upon us row reducing A until we find the identity matrix on the left. So if we can't do that, then not only will this method not tell us what the inverse is, but it will also tell us that the inverse doesn't exist. Because if A doesn't row reduce to an identity matrix, that means that either it's not one-to-one because one of the columns is missing a pivot, so we have a free variable, or it's not onto because one of the rows is missing a pivot. And if A was a square matrix to begin with, then both of those happen at the same time. Okay? Because if one of the rows is missing a pivot, that same column will also be missing a pivot. So A has to row reduce to the identity in order to be invertible. So this was an example of an invertible matrix. But we saw a matrix very similar to this one the other day, which was not invertible. It was this one. 1, 2, 3, 4, 5, 6, and 7, 8, 9. Now, we didn't talk about it in the context of invertible matrices. Instead, what was the context in which we saw something that looked like this before? What were we talking about? That's true of this matrix, because after all, when we row reduce this matrix, how many pivots does it have? It has only 2 pivots. There's one right here, and there's one right here, but that's it. So this matrix, when we row reduce it, has only 2 pivots. But when we first met 1, 2, 3, 4, 5, 6, and 7, 8, 9, we weren't talking about matrices. We were talking about vectors. Specifically, we were looking at the vectors 1, 2, 3, 4, 5, 6, and 7, 8, 9. And what were we claiming about these vectors? This would have been, I think was this yesterday? No, this was 2 days ago, I think. Yeah, there we go. When we last met these vectors, we were claiming that the set consisting of these 3 vectors was... It ended up being linearly dependent, exactly. So that should be a bit of a clue here, that we had these 3 vectors that were linearly dependent. When we stuffed them into a matrix, as the columns, it turns out that that matrix wasn't invertible. So let's just think about why that might be. What did we have to prove in order to prove that these 3 vectors were not linearly independent? What did we set up? We had to set up a vector equation with these 3 vectors and some arbitrary coefficients. And we had to show that that vector equation, if its right-hand side was the 0 vector, what did we have to show about that vector equation in order to guarantee that these were linearly dependent vectors?
X, Y, Z had to be coefficients that were not 0.
Exactly. There had to be a non-trivial solution. There has to be a solution where not all of x, y, and z are 0. X, y, and or z, not 0. In other words, the solution of this this vector equation, the solution had to be not unique. Right? In other words, there had to be a free variable. Or maybe more than one, we don't know. Right? And that's how we proved that these were linearly dependent. Right? In fact, we can see from the reduced row echelon form of this matrix that there is a free variable. Which variable is free here? Z, the column without a pivot. Okay. So we have a free variable. Z is free. And that's why A is not invertible, because we have a free variable. What is A not? What kind of a transformation is A definitely not? Because we have a free variable. 1-to-1. And because it's not 1-to-1, it doesn't have a pivot in every column, and because it doesn't have a pivot in every column, it can't row reduce to the identity. And because it can't row reduce to the identity, we can't find an inverse for it. An inverse does not exist. So the next characterization, then, of a matrix being invertible is, what do we have to know about the columns of A? If we want what's happening here not to happen. If we want a full complement of pivots. If I have a full complement of pivots, then how many free variables are there? None. If every column has a pivot, then all the variables are bound. And if all the variables are bound, how many solutions does this vector equation have? If all the variables are bound, this vector equation is going to have a unique solution. One and only one solution, namely the trivial solution. And therefore, the transformation is going to be 1-to-1. So we need that full complement of pivots to guarantee invertibility, because we want there to be only the trivial solution. And if there's only the trivial solution to this vector equation, what does it mean about those three columns? If only the trivial solution exists, they're independent. Exactly. So what we've argued here is that any square matrix whose columns are linearly independent will be invertible. By the way, this is the reason that this was a nifty way to start our class today. The transpose of an inverse is the inverse of the transpose. Okay, fine. But I can combine this fact with fact number 2 and say the following. If I know that the columns of A are linearly independent, what happens when I turn those columns into rows? Well, if the columns are linearly independent, and I turn it all sideways, then the rows are linearly independent. But a matrix A is invertible if and only if its transpose is invertible, according to this theorem that we proved. Therefore, a matrix is invertible if and only if its rows. A square matrix is invertible if and only if the rows are linearly independent. So that's another piece of the puzzle. Is that we need the linear independence of the rows. But in other words, we automatically get the linear independence of the rows if the columns are linearly independent. The last couple of equivalent conditions that will guarantee invertibility for a square matrix. I said these, but I didn't write them, so let me go back and write them. The homogeneous equation, AX equals 0, has how many solutions? Only one solution, namely the trivial solution. And then 0.5. By the way, this is equivalent to being 1 to 1. And then 5 is that the equation ax equals b must always be consistent. Always consistent. And that's equivalent to being onto. That's what we mean by onto. So a square matrix is invertible precisely when any one of these conditions is satisfied. Let me get them all onto one slide here. There we go. So as long as we require that A be a square matrix, and again, we needed A to be a square matrix so that it could simultaneously have a pivot in every row and every column, right? A square matrix A is invertible when any one of these conditions are satisfied, because any one of these conditions is equivalent to the rest. If A row reduces to the identity, then it must have a pivot in every column and therefore no free variables, and therefore the only linear combination of the columns that is 0 is the trivial linear combination, and therefore the columns are linearly independent. But the columns are only linearly independent if and only if the rows are linearly independent, because square matrices transposes are also invertible when the original matrix is invertible. But then again, the columns being linearly independent was equivalent to saying that the homogeneous equation has only the trivial solution. And the fact that there is a pivot in every row and the matrix being square guarantees that there's a pivot in every column, and vice versa. And therefore, since there's a pivot in every row, A represents an onto linear transformation, and so the equation ax equals b is always consistent. So any one of these is sufficient to guarantee that A is invertible.